Yeah, so my name is Sergey Shemyakov. I finished my PhD here at aix-marseille University, and what I will talk about today, the Transcendental Thurston theory, is a part of my PhD thesis that's still work in progress. And so the history of Thurston theory starts in the 80s when William Thurston answered the question which topological models of post-critically finite rational maps are realized by actual rational maps. And it was nicely written in the paper of Edward Hubbard in 1993. And well, this paper, I think, was mentioned quite sometimes already at the conference, for example, by Dylan. And this result had quite some importance for the world of complex dynamics. For example, using Hubbard trees, Fourier did the classification of post-critically finite polynomials as dynamical systems. Then similar classification was done for post-critically finite Newton maps by Loch, Mikulic, and Schleicher. And the similar result was also proved for critically fixed rational maps, so Hlushenko and Pilgrim, a couple of names to mention here. And when speaking about Thurston results, I cannot skip mentioning his big vision. So he had, except for the topological classification of rational maps, he also had two other quite important, quite big results. Capitalization of three manifolds and classification of surface automorphisms. The first, about the first problem, we had a nice introduction by John Hubbard on the very first lecture at the conference. And this was an important step in the geometrization problem that was finished by Grigory Perelman. And well, looking at this picture, I once again want to stress the subtle importance of complex dynamics for geometry, and in particular for hyperbolic geometry. Well, but I work on Transcendental Thurston theory. That's what I'm interested in. The attempts to generalize the rational theory were made ever since the 80s. I would say that the milestone publication was done in 2009 by Hubbard, Schleicher, and Shishikura. Exponential Thurston maps and limits of quadratic differentials. And in this paper, they answered the Thurston question for post-singularly finite topological exponential functions. And well, many people at the conference already explained to you about the post-singularly finite functions, post-critically finite functions. So these are the functions where the singular orbit or critical orbit is finite. And I want to mention at this point that all the functions that I will be considering in my talk will be post-singularly finite. And so this paper coined in a nice idea, the thick-thin decomposition for quadratic differentials. And it's quite a general tool that allowed them to tackle this transcendental case. So the next publication that I would like to mention is a PhD thesis by David Sprance in 2019. In this thesis, he generalized the theory of Hubbard trees to so-called homotopy Hubbard trees for all post-singularly finite entire functions. And the final publications that I want to mention are publications by Kostya Bogdanov, Infinite-Dimensional Thurston Theory and Transcendental Dynamics, which were put on the archive this year. And well, it's you will hear some more from Kostya. He will speak right after me. Oh, but you probably can notice that by looking at the schedule of our conference, that quite some talks go into the world of transcendental dynamics. And as you can see, the theory of Hubbard trees was promoted to the full power for entire functions. And the the tools that you can see in this exponential paper, well, they're general enough. So I want to make a statement that Transcendental Thurston theory is ready to blossom. Okay, so let's maybe get a bit more precise on what Thurston theory is. And first, you want to start with a topological model for some holomorphic or meromorphic function. And as an example, already it was on the conference. I have an example for topological polynomial. For example, topological polynomial is a finite degree branch covering of a plane to a plane, or a topological exponential. This is, as you can see on the slide, it's a topological cover of a plane to one's punctured plane. So when you have your topological model that you pick, you ask a question, can this for singularly finite topological model f be realized by some holomorphic or meromorphic function g, depending on the class that you consider. And the way to make it precise is by Thurston equivalence. So let's have a look at the definition on the slide. If we have a topological post-singularly finite function f, and then it's Thurston equivalent to some meromorphic or holomorphic function g, if we have the following diagram. So on the left-hand side, here you can see your topological function f from a sphere with punctured post-singular set to itself, to a sphere with the punctures. On the right-hand side, you see an entire meromorphic function g from a Riemann sphere with punctured post-singular set. And phi prime and phi double prime are two homeomorphisms which are isotopic relative to the set of post-singular points. Well, and let me maybe give a couple of ideas to the people who are new to Thurston theory. I won't go into too many details, but I just have to say this. The idea is a particular Thurston iteration, and you run this iteration on Teichmüller space. And the Teichmüller space, which was mentioned, for example, by Lasse in his talk, the Teichmüller space of a sphere with finitely many punctures, this would be the interest for us, is the space of conformal structures. So to be more precise, this is the space of homeomorphisms from one finitely punctured sphere to finitely punctured Riemann sphere modulo some isotopy equivalence relation. And the thing that we iterate on this Teichmüller space is a Thurston pullback map. And it was already advertised by Becca this morning. But let me draw the diagram on the slides for you. So you have, on the bottom of the commutative diagram, you have a phi n, which represents a point in Teichmüller space. This is some homeomorphism from punctured sphere to a punctured Riemann sphere. And on the left, you have your topological model f. So then you take the conformal structure from here, and you pull it back by the composition of phi n and f. And you uniformize this by getting the homomorphism here, and the diagram closes up with an entire function on the right-hand side. And we say that phi n plus 1 is a Thurston pullback of phi n, and this is defined on Teichmüller space. So a couple of notes here. You can see from this diagram that entire functions gn plus 1 are from parameter space of topological model f. And you can think about this. If you have a topological model for exponential functions, then gn's would be from an exponential family. And it's also, you can see from this definition that a fixed point of this iteration will give you the solution. If you have a look here, so the diagram will close up, and the function g on the right-hand side would be the Thurston equivalent function. Okay. Okay. So what's
the map phi n plus 1 is only defined up to post-composition with an automorphism of C bar, right. And gn plus 1 as defined has no dynamical meaning, because post-composition with an automorphism of C bar will destroy any dynamical properties that it should have.
Yes, that's true. We have to fix some particular points in our family by a basis. Yeah, that would be more correct. So it turns out that the Thurston problem has a positive solution unless there is an invariant topological multicurve with a particular impossible geometric mapping properties. And by topological multicurve, I mean a collection of simple closed curves with at least two punctures, at least 2 points from post-singular set inside and outside. And one kind of topological abstractions that will be important for my talk is a Levy cycle, also something that you've heard already. And a definition of Levy cycle goes like this: is if F is your post-singularly finite topological model, then a Levy cycle is a sequence of disjoint essential simple closed curves such that some component gamma I prime of the preimage of the curve gamma I plus 1 is homotopic to gamma I relative PF, right? This is your cyclic behavior. And this map from the preimage to image is a homeomorphism, so it's a 1-to-1 mapping. And the conceptual idea of my talk, if you have two entire functions that can be abstracted only with Levy cycles, then their composition can also be abstracted only with Levy cycles. So maybe that's a good point to ask whether you have some questions. Yes? I think as defined, well, the abstraction is a dynamic. The question was whether Levy cycle is a dynamical thing or not. And Dirk has an issue with me stating that Levy cycle is a dynamical object. Yes, well, this is the idea of my talk is a concept which I don't want to define precisely. This is just a taste of what you will see. So I don't want to digest this couple of lines on the bottom of the slide too precisely, because it will require me some talking and to get into the things that I don't want to get in my 30 minutes that I have for presentation. Okay, that's good. So first, I would like to speak about quadratic differentials. Quadratic differentials were the powerhouse of the exponential paper that I mentioned. And the reason for this is that the space of finite norm meromorphic quadratic differentials is cotangent to the Teichmüller space. And this was beautifully shown by John Hubbard on the first talk. Well, and why is this important for us? It's important because contraction in the cotangent space implies convergence in Teichmüller space. And maybe I can make an analogy here with something that we all are familiar with. If you have a rubber duck that swims on a d-2 dimensional pond, and you push it with a force that is ever decreasing, then at some point your duck will stop. And this is quite similar to what we do, but we do it in discrete time. So a conceptual takeaway of quadratic differentials is that they help to split the problem into functional question and dynamical question. Functional being how a particular function pushes forward the quadratic differential, and dynamical meaning what combining those push forwards along the orbit, what do they tell us about the dynamics of the function? And let me get a bit more precise. So a meromorphic quadratic differential Q is an object on a Riemann surface that locally looks like Q of z dz square. And this gives you the coordinate change between the charts on the intersect. Q is meromorphic, is a meromorphic function. And an important notion for me that I will mention a lot is the norm of quadratic differential, which I will be calling mass from now on. If we have a quadratic differential Q, then the norm on some domain X would be the following integral. norm of QZ, norm of DZ squared. This was expressed by John as dx dy. And a couple of properties of mass that will be important for me. So first, mass is zero on open domains. But also mass can concentrate on small domains. So for example, if you have a double pole of Q, then the mass around this double pole will be infinite. And if you have a couple of simple poles that come together, then the mass on the small disk surrounding them will be very big, and it will decrease exponentially away from the poles, at least in some neighborhood. Okay. And I also want to say about push forward of quadratic differential by holomorphic or meromorphic function. And a push forward is just a quadratic differential that is defined on the image Riemann surface. An important property for me would be this property with the composition. So the push forward by a composition splits into two consecutive push forwards. And also I will be speaking about how push forwards of quadratic differentials by functions affect mass of quadratic differentials. Injective push forwards by injective functions preserve mass, but usually some mass is cancelled. This means that this ratio that you can see here of mass of pushed forward differential to the original differential is usually less than 1. And I will say mass cancellation, that would mean 1 minus this factor. And the estimating mass cancellation is the main work which was done in the exponential paper. So maybe, again, other questions about quadratic differentials? OK. Oh, once again?
So I'm wondering if the push forward operator is always well defined in this case.
Yes, so infinite to 1 mapping still is perfectly fine with push forwards. The thing is, the push forward of quadratic differentials by a function may have many inverse branches. So you will have a couple of domains that are mapped on top of each other, and their quadratic differentials will interfere in some way, but it's still perfectly defined. OK, so maybe let me move closer to the main point of my talk. And the first definition that I have to give is a definition of a Levy disk. Again, this is not a dynamical definition. So let M be some modulus, and G be an entire function, and P be a finite set in a complex plane. And you may think about P as the post-singular set that we saw earlier. So let A be an annulus of modulus M, like on the picture, and C be its bounded complementary component. And we denote D as a pair AC, or sometimes we abuse the notation and we say it's a union. So the D is an M Levy disk for function G. If G is biholomorphic on the union of A and C, and A is essential with respect to marked points P. That means that there are at least 2 points from this set P inside and outside of the annulus A. So once again, the important things about Levy disks. They have modulus M. Function is biholomorphic, so it's 1-to-1 on Levy disk. And the annulus is essential with respect to our marked point. Okay, this is a Levy disk. And the next definition of Levy-type function is perhaps the most important definition in my talk. So I'll give it on various levels of details. So Levy-type functions are the functions where mass can survive the push forward without cancellation only on Levy disk. So being a bit more precise, if the mass loss in push forward of Q by a Levy-type function G is small, then almost all mass of Q is located on Levy disks for G of big modulus, and big modulus is important. Okay, so now to the precise definition of Levy type function. Let P be a finite set. And again, you may think about the post-singular set. And G be an entire function. Then we say that G is Levy type if for any quadratic differentials Q with poles in P, any modulus M, any fraction of mass outside disk epsilon, there is a fraction of preserved mass eta, such that once the mass cancellation is small, so the fraction of preserved mass is bigger than eta, then there are M Levy disks for function G of modulus bigger or equal than M, such that all but epsilon mass sits on these disks. And this definition might sound a bit technical, but in fact, in the exponential paper, it was proven that the exponential family of functions are Levy type functions. And another result that we have proven recently is that these multi-arrow functions are also Levy type functions. And if you have a look at the formula, it doesn't tell you too much. But in fact, functions of this kind, where P is a polynomial, are the functions with finitely many asymptotic tracks. And that's why they are of interest to us, and they really have some meaning. Okay? And why Levy type functions are so nice? It's because of the Levy disk principle. And Levy disk principle tells us if you have some topological post-singular function f, and we assume that all of the entire functions in its parameter space are Levy type, then such topological model is realized unless there is a Levy cycle. So Levy abstractions are only possible abstractions for function f, for which all the entire functions are Levy type. And here I have to apologize because it's the only slide in my presentation that requires some detailed knowledge of Thurston iteration. But I want to say a couple of words about the proof, about the ideas of the proof of Levy disk principle. All right, so assume that our function is not realizable. And this necessarily means that there is an efficient, so-called efficient sequence of functions gn and quadratic differentials qn along the orbit of our iteration in Teichmüller space. And efficient means that the ratio, this ratio of mass cancellation, well, this ratio goes to 1. Okay, and functions gn are Levy type, and this means that far enough along the orbit, almost all mass sits on Levy disks, like you can see here on the picture. And I hope people online can switch from the slides to the blackboard to see what I have drawn here. So here is the bunch of Levy disks for function gn, and we know that almost all mass sits on them, and they have big modulus. And we can map them forward by function gn into some other moduli, annuli of big moduli. And when we do this sufficiently many times, we map them around, and it necessarily has to happen for some Levy disk like this, that in a finite number of iterations that depends only on combinatorics of the function, it travels around, and its image comes back into its homotopy class. Okay, so this means that the core curve of this annulus has this cyclic behavior, and if you remember the definition of a Levy disk, the bihomorphicity of the map on it was a key point in the definition. So this means that all of the functions from between core curves will be one-to-one. And these red curves on the picture give you a Levy cycle. So this is the proof. If the function is not realizable, then you get your Levy cycle. Okay. So
So you're claiming here a theorem which 50 people have worked on 20 years. And I feel you were a little swift.
Okay.
I didn't actually manage to understand your definition of a Levy disk. I'd like you to go back to it. I mean, if you could actually justify that that theorem is true, well, you have a Fields medal coming to you.
That's an interesting statement. Okay.
I mean, it's not something to dismiss by just one slide.
Well, right. I would really love to go into the details of the proof and explain them to you. Unfortunately, I don't think that I have time for this right now. And also, I'm pretty sure that some of the people in the audience won't be able to really follow the discussion. But I definitely would be happy to convince you that this principle, which I don't claim to be proven at the moment, that this principle is true, and I'm really going towards the Fields medal. Okay. Yeah, but let me maybe quickly.
Part one, we've all known.
Yes. Well, my claim would be that the Levy disk principle is somehow, you can already read this through the lines in the exponential paper at this moment. So I don't think that this is such a groundbreaking thing. But again, let's maybe discuss it a bit afterwards. Because if the Levy principle is a dynamic type statement, then the following theorem that actually came to be a theorem is a functional statement. It does not involve any dynamics. And it tells you if f and g are two Levy type functions, then their composition is also Levy type. Well, and we kind of.
So I gather that the condition, that what makes this not absolutely revolutionary is the hypothesis that all the functions Gn are of Levy type.
Proving that all the functions are of Levy type is really all the work that has to be done in order to put this to practice.
Okay, so that's really the hypothesis that makes this theorem.
Right.
Okay.
Okay. Yeah, so let us get back to our functional statement. And I was saying that we already kind of used this theorem as an idea for the Levy disk principle. So assume that the mass cancellation for the composition is small. Then the mass cancellation for each of the functions must be small due to the properties of push forwards that I mentioned earlier. So you take the Levy disks, you take the Levy disk of function g, and you map them forward. And the disks, well, kind of you can see it on this picture. The images of the disks will be almost the Levy disk for the next function f, just because they share almost all mass of quadratic differential q. And then you have actually to think a bit about the geometry of what's going on. And you have to tweak the mass cancellation ratio eta, but in the end, you can get arbitrarily big modulus and arbitrarily small fraction of mass outside of the Levy disk for the intersection of these images of Levy disk for G and Levy disk for F. So this is also, I wouldn't call this theorem a groundbreaking result. But what do the Levy disk principle and the Levy composition, the Levy disk composition theorem seem to imply is that if you have two functional families for which, for each of them, Levy abstraction are the only possible type of abstraction, then for their composition, also Levy abstraction should be only possible type of abstraction, and your topological model should be realizable otherwise. Okay, so where do we go from here? one goal is to put more functions in the Levy type. This is perhaps what John would be excited to hear about. And I also work on this in my PhD thesis. So this will be in the thesis as well. There is some more work coming in this direction. So the next thing, you can actually add critical points to the framework of Levy disk. If you remember, Levy disks mapping 1-to-1 was an important piece of definition, but you can actually relax it. You can allow for branched mappings, and you can develop the theory of so-called branch disks and branch disk principle. And for example, this helped me to get a proof for trigonometric family, which, as you can see, is a composition of a function with two critical points with exponential Levy type function. And yeah, maybe a small remark here. You see that the rational function has a pole, but the composition is entire. And I work with entire functions. It would be sufficient for me to have an entire composition. Well, and the final and perhaps the most ambitious goal for me is to add the poles into the framework of Levy disks. So this would require quite some work, because we should see all the other possible obstructions, not only Levy cycles, but yeah, all the other abstractions. They come with poles, and this will require understanding the rational paper by Dewey and Hubbard well enough. So this is that's a challenging task, but at this point we believe that this should be doable. So I hope I told you some interesting stuff about Transcendental Thurston theory, and even for people who are not really aware about Thurston theory too much before this conference. And thank you for your attention.